on those topics, on fuels and on heats of reaction. So you are going to get those emailed to you, I believe. But I'm a firm believer in working from scratch to explain something rather than just handing people a whole load of notes and them just being bamboozled by all the words and all of the typing and so on and so forth that exist. We will have a what do you call it, an opportunity to what do you call it? We will have an opportunity to ask questions at the end of this session, or maybe halfway through. I'll stop and see if there's any what you call it, particular questions that you'd like to ask. But as I had advertised on TikTok, it's mainly for question 6 because it's one of the most popular questions on the paper, and it's on fuels and heats of reaction. So what I'm going to do now, and I just need to explain this to you, is that when I share my screen with you and I start writing on my notepad, you're probably not going to be able to see me, which is probably something that you will be quite pleased about. So it'll all be focused on what I'm writing. And this is recorded, so this is going to be available to you to look back over at your leisure. So if there's anything in particular that passes you by, you'll be able to, go to it, slow down and so on and so forth. Do you know what I mean? Or what you call it, pause the session and so on and so forth. So I'm going to start first of all talking to you about question 6 and its general layout. And as with all questions, obviously things need to be practiced, and the more practice you do, the better you get at it. So here is my trusty notepad and my pen, and we're going to pop on to question 6. Now, for the last 20 something years, question 6 has been on the topic fuels and heats of reaction. So we'll assume that they're not going to make a change to that this year, because in the early days of the syllabus, back in the early 2000s, sometimes the material that I'm going to talk about tonight might have been split into a half a question on question 10 or 11. The good news is that there's going to be fuels and there's going to be heats of reaction involved. So the first thing we're going to talk about, folks, are the fuels aspect of it. And with regards to fuels, the first part is natural gas. Right? So natural gas, folks, you're looking at molecules that have between 1 and 4 carbons in them. It won't be a gas once the molecules go bigger than 4 carbons. So we're looking at methane, ethane, propane, and butane. Now, natural gas in Ireland, so this part of the world around Ireland, is mainly methane. And that's good, right? Mainly methane, CH4. And the reason why that's good is because it's a clean fuel. So we don't get an awful lot of of soot or dust or smoke particles, from it. And it has a high kilogram calorific value, meaning you get a lot of energy from it. So as a fuel, that's very good. Another advantage is it's stable. So if you were asked about methane, in what way, what's the advantage of it? It's a clean fuel. We don't get a lot of soot. It's got a high kilogram calorific value, meaning we're going to get lots and lots of energy from it, and the fact that it's stable. I like the fuel that's in my house to be stable so that I'm not worried about it spontaneously combusting and the house blowing up at 4 o'clock in the morning or whatever it is. So having a stable fuel is a very, very good idea. And the reason why your methane is stable is because it's saturated, right? It's all single bonds around the carbon and it's saturated. Now, if we go to the USA, so if we go over to the USA, it's mainly propane and butane. And this is a question that they've asked several times. And let's have a look at what I mean. Over here in this part of the world, that's sold as LPG, liquefied petroleum gas. And if we go back in time, they have asked you what do the letters LPG stand for. So liquefied petroleum gas. Okay. And if they ask you what are the main components of liquefied petroleum gas, well, you're going to go back and you're going to go propane and butane. And as I said, they have asked that question quite often. The other thing about natural gas, there's not a lot we need to learn about it, really, to be honest with you. The other thing that we need to learn about the fuel natural gas is that it is odorless. So no smell. So they add sulfur compounds called mercaptans, mercaptans, TANS. They add mercaptans to give it a smell. So these contain sulfur. So there's going to be no, no mistaking the fact that you are smelling these molecules. They don't smell like anything that you would normally smell if you're walking around the place. So they contain sulfur, and that's going to alert you to leakages. And again, that is something that on question 6, they have asked on more than one occasion. So mercaptans, sulfur-based compounds that are very strong smelling, very distinctive smell, and that's going to alert you to any leakages that go on. Now, essentially, with regards to natural gas, that's about it. There isn't too much more that they can ask you on that particular topic. The other fuel that we're going to look at is one which is crude oil. And crude oil, folks, is the one that they are going to ask mainly about. Crude oil, which is known as petroleum. And when petroleum or crude oil comes up out of the ground, it's very thick, it's black, it's very pungent, meaning strong smelling, and it's useless in the way it comes out of the ground. So crude oil, useless in its natural state. Absolutely no good whatsoever in the natural state, right, that it comes out of the ground. So it needs to go to be refined. And they refine it in an oil refinery. And what they're going to do when it goes to be refined is they're going to make it useful. That's the whole point of it. We want to make something useful out of it. Now, these compounds are going to be so useful, folks, that people are going to be willing to, to fight wars over, right? So crude oil in its natural state is useless, going to send it off, and it's going to be refined, and that's going to make the crude oil very, very useful. One of the most common questions with regards to crude oil is what exactly or how do we refine it? So what is the process? How do we refine crude oil? And you need to know the name of the process. It's called fractional distillation. Now, this is the most likely part of this fuels section of our course that we're going to get asked about. Fractional distillation of crude oil. And one of the questions that they've asked more than one occasion in the past is to describe with the aid of a label diagram how this is carried out. But before that, we're going to talk about the principle. How does it work? So the word separation, folks, right? Chemistry is kind of an unforgiving subject. They are looking for keywords or key phrases. If you don't have them, you can't get the marks. So the key word in my principle of fractional distillation of crude oil is separation of oil into different parts or different fractions, different components. They'll accept any of those words, right? Into different parts or fractions. And that is based on different boiling points. So we're separating them based on the molecules having different boiling points. So again, if they ask you, how's it working? Or another way that they have questioned this is they said, what's the property of the molecules that we're using when we carry out fractional distillation? Well, the property is the fact that they have different boiling points. So separation of the oil into different parts based on them all having different boiling points. And the key words there, separation and boiling points. So describe with the aid of a label diagram. Now, I would see students and they will spend ages staring at a diagram and think that they've learned it. So folks, there is no, and I mean absolutely no way that you can learn a diagram without practicing it. So if you haven't practiced a diagram about 4 or 5 times before the day of the exam, chances are you're not going to get full marks in it. So again, my advice would be you want to take out a page, you're going to draw the diagram, you're going to practice it. Even if you're drawing it along with me now, at least that's one time that you'll have done it. And it might be, one more than you've ever done it before. So practice drawing your diagram. So the way I go through this is I start off, I have a barrel of oil, not that oil is always in a barrel as such, but we have a barrel of oil and that goes into a furnace. So it's going to be heated, right? And the furnace is somewhere around 500 degrees Celsius. So in other words, it's really, really hot. So the oil is going to pass into a furnace. And from the furnace, this is the important bit, it's going to be piped into a massive, tall tower. So give yourself plenty of height on your page so that you can draw a nice tall tower. And on the right-hand side, it's very important that we show tubes coming out of the tower, right? Because remember, we're separating, so we need to show where each fraction, each part is going to be piped off to a different storage container. So at the end of each one of these pipes, folks, there is a storage container waiting to collect the fractions of crude oil that we're separating, right? So we're going to have several pipes, and in the marking scheme, that's what they're going to be, what you call it, looking for. If there are no pipes on your diagram, well, then you've missed the point, because the whole point is you're separating and you're going to store them all separately from each other. So we need to pipe them off to different storage containers. All the way up along the tower, we have these trays or these shelves, and the shelves have little openings. Now, there would be many more that I'm going to draw in my diagram, but as long as I have a few in my diagram, right, they will give me the marks for it. So you must show these shelves or trays, and I'm just drawing a shelf on each of my, beside each of the pipes that are going off, right? The next part with the diagram is the fact that, and I would, make a big deal out of this. So maybe a different color pen, something like that, just to mark, right? As you go up the tower, I'm going to turn it around and we'll go, the temperature decreases. Because if we don't show that, we're missing the point. So therefore, it's hotter, right, at the bottom than it is at the top. So it's cooler at the top. So we need to keep that in mind. The temperature is decreasing as we go up, what you call it, the tower, right? The tower is about 80 meters high, 80 meters in height. So it's a big, tall tower from bottom to top. Now, what's going to happen is your oil has gone through the furnace. It's going to come in here. The molecules that are not gaseous at this really high temperature are going to end up down here. We call these the residue fraction. We need to know the name and we need to know the location in the tower. So the residue fraction, we're looking at about 40 carbons plus. They're the biggest molecules of them all in the residue fraction. We'll talk about uses for these now in a minute. I then generally go top of the tower. So if we've the biggest molecules at the bottom, we're going to have the smallest at the top. So that's your C1 to C4, and that's called the gas fraction. And again, once you go bigger than 4 carbons, you're not going to be a gas, right? Okay, so C1 to C4, gas fraction. The next one is C5 to C10, which is called the light gasoline fraction. And it includes naphtha, NAPHTA, which is C7 to C10. Now, I get students all the time going, do I need to know the numbers of carbons? Yes, you do. They can ask you, what name is given to the fraction containing between 5 and 10 carbons? You'll go, like gasoline. What name is given to the fraction that has between 7 and 10 carbons? You'll go naphtha. So we do need to know those. Next fraction down, right? C10 to C14, that's our kerosene fraction. So again, bigger molecules, we're going from lightest down to bigger ones. Next one down is about C14, we'll say to C25-ish, and this is called the gas oil fraction. And then from about C25 to about C40-ish, we've got the heavy gas oil fraction. Now, in recent years, They're very interested in finding out whether you know the position of these in relation to each other. So they might say, describe with the aid of a label diagram fractionation or fractional distillation of crude oil. And in your diagram, show where the kerosene fraction will be, show where the light gasoline fraction will be. So we need to make sure that they are in the right location in relation to each other. So gas, lightest, residue, heaviest, and light gasoline with naphtha, kerosene, gas oil, heavy gas oil. To be honest with you, the gas oil and heavy gas oil, they don't ask too many questions about, but the others, they do. So this is the diagram. You're going to get full marks if you have that. You've got the heat, you've got the temperature decreasing, you've got all the pipes coming off, and we have all of our fractions in the correct location in relation to each other. They are not looking for, do you know what I mean, an artist's impression of a fractionating tower. They just need to have something that is clear and shows what's actually happening. We are separating the crude oil based on everything having different boiling points. Because what's going to happen here is in comes the molecule. Let's say at this temperature, it's really hot, so it's a gas. So what does it do? Or what does it do? It rises up. And then it rises up. Keep going. Now remember, the temperature is decreasing. So let's say the molecule gets to here, and all of a sudden, the temperature is below its boiling point. So what's it going to do? It's going to turn into a liquid. Once it reaches a temperature below its boiling point, it'll turn into a liquid. Now, because of these caps on top of the openings, it can't fall all the way down to the bottom of the tower. So where's it going to go? It's going to fall into this shelf. Who's going to be in this shelf? Molecules with similar boiling point, molecules with similar numbers of carbons as a result. So that's how we're separating it. So if you have between 10 and 14 carbons, you're going to turn into a liquid somewhere around here at whatever this temperature is. We don't need to know the temperatures. We just need to know that the temperature is decreasing as we go up the tower. They like asking us for uses of our fractions, folks. So the main ones, and you should know at least one, all right, okay, so your gas fraction, which is your 1 to 4, is fuel, right? Fuel and LPG. So remember, LPG, liquefied petroleum gas, made up of propane and butane. Remember, it has no smell. They can ask you about mercaptans, right, in the gas fraction. So it doesn't have to be natural gas coming from a gas field. It can be the gas fraction from your fractional distillation of crude oil. Underneath that, we had the light gasoline fraction and naphtha. Right? And the light gasoline fraction and naphtha fraction are very important because that's where we get petrol from. So they give us petrol, and we need to learn all about petrol now in a while. So that's going to be really important there. Right? Kerosene. Your kerosene fraction, folks, is where we get aviation fuel. So airplane fuel. Right? Our aviation fuel is in our kerosene fraction, and paraffin oil. Now, paraffin oil is colorless oil, and it doesn't freeze at low temperatures. So if I decided I was going to climb Mount Everest in the morning, which I'm absolutely not, but if I were to decide that, I'd be bringing paraffin oil with me. I can burn it to produce heat, to keep me warm. I can burn it to produce a flame, to melt snow or cook whatever, or heat up whatever it is I want. And unlike a lot of fuels, it's not going to freeze at those very low temperatures. It's going to stay as an oil. So it's going to be helpful in that way. Right? So paraffin oil, kerosene fraction. Now your gas oil and heavy gas oil, we can kind of clump together. And these would be lubricating oils for engines. So big engines, obviously the parts that are going to be in contact with each other, we don't want them scraping off each other. We want them to move smoothly. So that lubricating oil for different engines is going to be very important there. And then the one that they also ask about is residue. So residue, it's used as bitumen, bitumen, which is the tar that's used for road surfacing. So obviously we've a lot of roads on planet Earth, so we need a lot of tar, and we're going to be replacing them. So bitumen, right, the tar for road surfacing, but also, right, there are only so many roads on planet Earth. So therefore, we can also do the following, and we can carry out a process which we're going to talk about again in a minute, which is catalytic cracking. Now, catalytic cracking is where you break long chained molecules into lots of shorter ones. Long chained molecules into several shorter ones. And the reason why we do that, folks, if you want to note, long chained molecules, there's only so much you can do with them, as in you can road surface, but there's a greater demand for short chained molecules. So economically, that was a question one year. What's the economic importance of catalytic cracking? Well, there's a greater demand for shorter molecules. And if there's a greater demand, people obviously are going to be willing to spend more money or pay more money for those. So that's why we want it. Long chained molecules, not so much high demand, low demand, whereas short chained molecules, very high demand, and as a result, economically, that's going to be important. So make sure that you know a use for each of those. Now, what else can we talk about? Well, we need to talk about petrol, folks. Now, petrol comes from your naphtha and your, your light gasoline petrol. So petrol. We're looking at molecules, anything from C5 to C10, right, in petrol. And, the petrol that we use needs to ignite with air in a certain compartment in the car engine. And if it ignites with the oxygen in the air in the wrong compartment, so in other words, if it ignites too soon, meaning before it should, in the engine, we get a thing called auto-ignition. Now, auto-ignition is known as knocking. Those two words are interchangeable, auto-ignition or knocking. The reason why it's called knocking is because, you hear this, sound, which sounds like knocking coming from your engine, and that cannot be a good thing, folks. If you've got a knocking sound coming from your engine, there are pressure changes happening inside in your internal combustion engine, happening in a chamber where they should not be happening, and that is not going to bode well for your engine long term. So you could be bombing down the M50, obviously at the speed limit, and your engine could decide, today's the day I'm going to give up, and you've got loads of other cars around you, so that's potentially extremely dangerous. Never mind, really expensive. So we do not want the petrol and the air to ignite in the wrong chamber of the car's engine. So if you're asked to define auto-ignition, it's the early explosion, it's the early ignition, it's when the petrol and air ignite too soon in the engine, you get auto-ignition. Now, what causes auto-ignition is poor quality petrol. And poor quality petrol is going to be made up of the following. It's going to be made up of long-chained hydrocarbon molecules. So long-chained hydrocarbons, and they're going to be straight-chained, as in they're not going to have any branches on them. So they're going to be long and they're going to be straight-chained molecules. And both of these things do not make for a good quality petrol. Long and straight is going to cause auto-ignition. So what do we want? Good quality petrol. We'll have the following features. Good quality petrol. The molecules will be short-chained. They'll be branched, so they'll have loads of carbons coming off them. So branched, chained, and something that we haven't mentioned, they will either be cyclic or aromatic. So these are the features of, the molecules that give you a good quality petrol, and I've lost count of the amount of times that they've asked for these. So, right, the shorter the better, the more branches the better, and if you're cyclic or aromatic, that's good. Cyclic is something like cyclohexane, which is a hexagon. Aromatic is something that contains benzene, which is a hexagon with a circle in the center. So cyclic and aromatic do not mean the same thing, right? Cyclic means that the carbons are in, a circle, but they're not necessarily containing a benzene ring. Aromatic means they have a benzene ring in their structure, right? So good quality petrol, short, branched, cyclic, and or automatic. And if you have those in your fuel, that's going to be great. Now, how do they decide whether your petrol is good or bad? They're not going to put it into an engine and listen to see does it have knocking or not. So it gets assigned what we call an octane number. And again, this is a definition that comes up all the time. And even with my own students there, I asked this in their mock exam, and there would be not too many, but a few that missed out on a key word. It's a measure. It's a measure or measurement. And if you don't have the word measure or measurement in the definition, then you're not getting the marks. A measurement of a fuel's tendency to not auto-ignite. Right? To not auto-ignite. The higher the number, the better. So for example, good quality petrol has an octane number of around 97. So up in the high 90s, that'll give you a good quality petrol. Anything, do you know what I mean, down in the 80s and whatever, you're talking about trouble for your engine, as I said, in the long term. Now, where do they get these octane numbers from? Well, there are two what we call reference molecules. And in exam questions, they'll refer to them as reference molecules, folks. So my two reference molecules for assigning octane numbers, and again, remember all of this, right, that I'm talking about is in the handout that you're going to get, right, okay, for signing up for this class in the first place. My two reference molecules, one of them has 7 carbons, 1, 2, 3, 4, 5, 6, 7, in a straight chain, and it's going to have 16 hydrogens, folks. So it is an alkane with 7 carbons, 16 hydrogens, long, straight, definitely going to cause autoignition if I had a fuel full of this. And this is called heptane. Heptane, right? C7, H16. If you're not familiar with it, learn how to draw it, learn how to name it. And this guy is assigned an octane number of 0. We only have to know 2 octane numbers, one for each of our reference molecules. And this guy is assigned an octane number of 0. Why? Why is it so bad in terms of its octane number? Well, it's long and it's straight. It has no branches. There is nothing cyclic about it. There is nothing aromatic about it. That molecule, if you burned it, will cause autoignition. So that's what we have chosen to be one of our reference molecules. The other one has 5 carbons in its main carbon chain. 1, 2, 3, 4, 5. Now, I'm going to go from left to right. So on the second carbon, I'm going to put a carbon above and below. So now what I've done is I have created 2 what we call methyl or methyl, depending on where you go to school and how posh you are. So me from North Cork, it's definitely not posh. So we have 2 methyl groups attached. And then if that's carbon 2, folks, I'm going to go to the 4th carbon and I'm going to put yet another methyl group. Now, a recent development, folks, since last year is when you draw your molecules, they want you to draw all the bonds all the time. So they don't want you to write CH3 anymore when you're drawing your molecules. Right? So all the bonds all the time. So if that's not something that you've been doing, well, then maybe you might start doing it. So this guy is called 2, 2, 4 trimethyl pentane. 2, 2, 4 trimethyl pentane. So it has 8 carbons in total. 8 of them in total, right? The 5 here plus the 3 on the branches, right? And it's going to have 8, 2, 6, it's going to have 18 hydrogens. Now, I could write its formula, CH3, then C, CH3 with a 2 after it for these two. then CH2 for this one, then CH and a CH3, and then CH3. So you might see its formula written out that way. And when you start seeing CH3s in brackets like that, that should alert you to the fact that it is 2,2,4-trimethylpentane. That guy, folks, is shorter, so 5 carbons in the chain, short, and it's got several branches. 3 methyl groups are the branches. So this guy is assigned an octane number of 100. Now, you can have octane numbers higher than 100, but this guy is assigned an octane number of 100. And they are our 2 reference molecules. And you are regularly asked in question 6 to draw them and to name them and to state their structural features that result in them having the octane numbers that they might ask you to assign. So 2,2,4-trimethylpentane, short, loads of branches, high octane rating. Will not cause autoignition. Heptane, long, straight, no branches, definitely not good, so is going to cause autoignition. So what they do is I, strike oil later on this evening in my back garden. I send it off to an oil refinery to be separated into its very useful fractions, because everybody's going to want to have those fractions, so I'm going to be a millionaire as a result. And my light gasoline and my naphtha fraction, I want to sell as petrol, and I'd like to know, does it have a higher low octane number? If it's got a high octane number, I don't have to do anything to it. I can sell it and make my money. If it's got an octane number that's not so good, it's going to cause autoignition. Nobody's going to want to buy it. So what am I going to do? I'm going to have to solve the autoignition problem. So what they do is they burn tar as petrol, and they look at how does it burn, what energy does it give off, what are the emissions, etc., and they match it to a sample of these 2 mixed together. And if you had a sample of these 2 mixed together where 10% of it was heptane and 90% of it was octane, 2,2,4-trimethylpentane, it would have an octane number of 90. So if it's a 1090, then it has an octane number of 90. The octane number is telling you the proportion of this branched, shorter molecule that's present in it. So they'll assign my petrol an octane number. I'll be hoping that it's up there in the 90s. If it's not, well then what am I going to do? I'm going to have to do something about it. So again, this is regularly on question 6, folks. They are solutions to autoignition. So let's say they find my petrol is not great. AUTOIGNITION. Yeah. Solutions to autoignition are knocking. So what can I do to my petrol to stop it from knocking? Well, first of all, we can do additives. Now, I want you to be very clear, that we're going to split these up into 2 types. I can add things in, hence additives. One of them is a compound called tetraethyl lead. And tetraethyl lead is toxic. So environmentally, that's not good. Now, please avoid when you're asked, why do we not add tetraethyl lead? Don't you mean anymore? Saying something really wishy-washy like lead is bad for you. As I keep saying to my gang, don't you mean too many sweets, too many ice creams are bad for you. So we're not interested in that. We want to show them lead is toxic, right? It is a really toxic heavy metal. We definitely do not, want to have it in spewing out of the emissions from our exhaust fumes into the air for us to breathe and for us to come in contact with. Right? Also, the second reason is lead is a catalyst poison. And it'll poison the catalyst in the catalytic converter of a car. And we definitely don't want that to happen. We've paid thousands to have a catalytic converter in a car. And now if we use really, leaded petrol, right, we're poisoning the catalyst, and we might as well have taken those thousands of euros and thrown them down the drain. Right? There's no point, if you're going to use leaded petrol, in having a catalytic converter in a car. Now, since 1993 in the European Union, it's law that every car has a catalytic converter, which is why back in the mid-80s, early 90s, they got rid of leaded petrol. Gradually, they offered scrappage schemes to get rid of older cars so that we could bring newer cars in that were going to be what you call more environmentally friendly, and we could get rid then of the lead in the petrol. So in my catalytic converter, CO, which is poisonous, is being converted to CO2. NO, which causes acid rain and will also destroy ozone 24/7, that's going to be converted to N2. Now watch those. They're the two conversions in a catalytic converter. It's CO to CO2. It's NO to N2, not to NO2, folks. A lot of people will make that mistake. And your catalysts in a catalytic converter are platinum, palladium, and rhodium. And they are all as expensive, if not more expensive than gold. So they are really, really expensive metals, right? And they're pretty unreactive, so they're not going to cause any damage. They're not, do you know what I mean, going to damage the environment as such. But, folks, all right, they will be destroyed by the lead of the tetraethyl lead if we use leaded petrol. So we need to avoid that from happening. So that's one additive. We don't use it anymore. We're very lucky to live in a part of the world where that's not done anymore. The other additive are things called oxygenates. Now, a question I often ask my students are, what are oxygenates? So they're molecules like alcohols and ethers, ETHERS. And we don't really study ethers other than mention them here, but we do alcohols, right, in other parts of our course. So they're molecules like alcohols and ethers that contain oxygen, as in the element oxygen, right? They contain the element oxygen. So alcohols will have an oxygen, ethers will have an oxygen in them. So why do we add them? What is it that they're going to do? Right, okay, they increase the octane number. That's why we add them. The whole point is we want to bring the octane number up so that autoignition doesn't occur, right? But these guys have an added benefit. They reduce CO emissions. Now, CO, folks, is carbon monoxide, and carbon monoxide is a toxic poisonous gas that's found, for example, in cigarette smoke. So they reduce carbon monoxide emissions. So obviously that's much, much better for the environment. Petrol that has oxygenates added usually is going to cost a couple of cents extra per litre because it's going to be better for your engine, it's going to be better for the environment, and as a result, they're going to lob that charge onto the consumer. But oxygenates, molecules like alcohols and ethers. They might ask you for an example, so you can go methanol or ethanol. In Brazil, they've loads of sugarcane, so they ferment it and they produce lots and lots of ethanol, and they have massive amounts of it, so they use biofuels. So they add that oxygenate into the fuel, and they're reducing the amount of carbon monoxide in the emissions, plus it's better for your engine, do you know what I mean, as well. If it's ethers, you've got things like methyl tert butyl ether, which we can shorten to MTBE. The full name for that will be in the handout when you get your hands on that. So methyl tert butyl ether, that will also increase the octane number and reduce the emissions. Now, again, folks, they are additives. Additives. You are adding them in to the fuel in order to improve the octane number. The next three are called reforming methods. So reforming means you're changing the structure. You're changing the actual structure. So remember, long and straight was not good, short and branched is good. What else was good? Cyclic or aromatic. So you need to know the names of these guys. First one we're going to talk about is isomerization. Now, we know that isomers are molecules, same molecular, different structural formula. So if I take, do you know what I mean, something like, and this is one that they've given in the past, if I take something like pentane, so there's pentane, right, which is, you know, straight, no branches, not cyclic, not aromatic, and don't forget to fill in all your hydrogens, folks, all right? So if I take something like pentane and I carry out isomerization, what I'm going to do is I'm going to take one molecule of pentane and I'm going to make it shorter. and it's going to go from 5 carbons to 4, and I'm going to have the 5th carbon as a branch. So there's an example now of isomerization, because I have the same numbers of carbons and hydrogens, but I have a shorter with branches, or a branch, so that's going to have a higher octane number. Now what I want you to note is that it's a 1:1 ratio. One molecule that's long and straight becomes one molecule that's shorter and branched. This is just an example of isomerization. They don't have to use pentane, but they have used it in the past. Next guy is called catalytic cracking, which we've already met. Now that's where you take one long molecule, and remember there's low demand for this, and we're going to break it up into more than one shorter and possibly branched molecule. So if you're going from long and straight, one long straight molecule, and we're making it into more than one. So it could be 2, it could be 3, it could be 4, it could be 10, but it's more than one. So it's not a 1:1 ratio, it's a 1 is to more than one product. So whether that's 1:2, 1:3, 1:5, one long straight into more than one shorter and possibly branched, what's after happening? We've gone from long straight, which will cause autoignition, to short and branched, which won't cause autoignition. And the final one is one with a lovely name that you're going to have to remember: dehydrocyclization. Dehydrocyclization. Two features to this, folks. We take long straight, and we first of all turn it into cyclic. So long straight goes to cyclic. Second stage of this dehydrocyclization is to take the cyclic and change it into something aromatic. And the added advantage is you also get hydrogen gas, extra fuel. So you've increased the octane number because you now have something aromatic, and that doesn't cause autoignition. And you have a co-product, which is itself a fuel. So you've got an added bonus in dehydrocyclization. So you're going from long to cyclic, and then from cyclic to aromatic plus hydrogen. They're the two features of dehydrocyclization. And again, they do quite like asking questions, you know what I mean, on that topic. They like to ask you, you know what I mean, how you're going to, what to call it, how you're going to improve the octane number. So we've had two additives. One we don't add anymore because lead poisons a catalyst and it's a toxic heavy metal. The other one is oxygenates, which we do, which is adding alcohols or ethers so that we get less carbon monoxide and we improve the octane number. And then we have the three reforming methods. The three methods where you're changing the total structure of the molecules. And what you're doing when you're changing the structure is you're making sure that you are going from long and straight into something shorter with branches, into several molecules that are shorter and possibly have branches, or you're changing something long and straight into a molecule that is going to, become cyclic. And then by taking hydrogen off the cyclic molecule, you end up with hydrogen gas. So you go from cyclic to aromatic. So we'll give you a couple of examples here. This is 2015 question 6. Every fraction separated in the refining of crude oil is a mixture of hydrocarbons. Give me a property of a hydrocarbon that results in its presence in a particular fraction. Well, I mentioned that earlier on in the session, is that the fact that they all have different boiling points. That's how it's going to end up in with other molecules. They're all going to have different boiling points. Name the fraction obtained from crude oil that's used as fuel for jet aircraft. So that was your kerosene fraction, so we needed to know that. And then what process is used to convert molecules in this into smaller molecules that are in greater demand? So what was the name of the process that made longer molecules into smaller molecules that were economically more beneficial, that were in greater demand? That's your catalytic cracking. Now, we've written the word boiling points, we've written kerosene, and we've written catalytic cracking, and we've got 11 out of 50 marks, we're on 22%. What are the two reference hydrocarbons used to assign octane numbers to fuels? What are they? They're not asking you specifically to draw them or to name them, so they're happy if you do either or. What are the two reference hydrocarbons? Heptane, 2,2,4-trimethylpentane. And because they said what are they, doesn't matter whether you draw or name them, but please watch out because they catch people out with that all the time. They ask you for the name, people give the formula, or vice versa. Give two advantages of adding oxygenates like ethanol to petrol. Two advantages. Well, number one, why do we do any additive to a fuel? We do it so that we are increasing the octane number so we don't get auto-ignition. That's the same point. Increase the octane number so that we don't get auto-ignition. And what's the other advantage to adding oxygenates, specifically oxygenates? Well, they reduce the levels of carbon monoxide in the emissions. So obviously it's more environmentally friendly. So there's, a few examples touching on what, we've talked about there so far. And what you do is you go to question 6, and the more question 6 you go to, the more you're going to see, how this works. So this is from 2017. They wanted me to write a balanced equation for the dehydrocyclization reaction in which heptane is converted into methylbenzene and hydrogen. Heptane into methylbenzene and hydrogen. Now, we want an equation. They've told me to start with heptane. They've told me to end with methylbenzene and hydrogen. So that's what I'll do. So we'll start with heptane. 1, 2, 3, 4, 5, 6, 7, with all of those hydrogens that go with it. We're to get methylbenzene. There's a benzene ring, folks. Hexagon with a circle in the center. Methyl group attached. CH3 group attached. And they told me get hydrogen, H2. Now, in the earlier part of your organic chemistry studies, where you study alkanes and aromatic compounds, these would be molecules that you should be well used to drawing. And if not, well, the good news is you've got time now to learn them. That's why you're here tonight. You're going to go away and you're going to learn them. So there's heptane and there's methylbenzene and hydrogen. If I count all the C's here, there are 7. If I count all the H's around here, I've got 16 H's. If I go to methylbenzene, folks, I have 7 carbons. I'm going to show you where those 7 carbons comes from. We've got 1, 2, 3, 4, 5, 6, 7. There's where the 7 carbons are. 6 on the benzene ring, right? And 1 in the methyl group. How many hydrogens? We've got 1, 2, 3, 4, 5. I know you can't see them, but every corner on a benzene ring is a C and a H, except for this one up here. It's a C bonded to a C, so the H was taken away. So we've got 5 on the benzene ring, 6, 7, 8. So we're going to have H8, and then hydrogen gas, folks, is H2. Hydrogen cannot exist on its own. So hydrogen gas, H2. So how am I going to balance this now? Well, my carbons are balanced. I've got 16 H's over here on the left. I want to have 16 on the right. This guy's got 8. So if I put 4 in front of that, I now have 8 and 8, which is 16. So there's your balanced equation for, and there's an example of your dehydrocyclization. And then they asked you, what's its purpose in oil refining? Why do we carry it out? What's the purpose of dehydrocyclization? Well, it's there to make sure that, right, its purpose is to make sure that we improve the octane number of the fuel, right? It's there to improve the octane number of the fuel. So there are lots and lots of questions like that, which folks you're going to have to, work your way through, right? And every question 6 then, right, except for 2007, there is an exception for that. Every question 6, except for 2007, is going to have a heat of reaction, which I'm going to show you how to do now. Now, this is a question from 2013, and you can see their definition of octane number, measure of a fuel's tendency to resist auto-ignition. They've given me 2 molecules, A and B. They've said A is obtained from the fractional distillation of crude oil and it's converted to B by isomerization. So A has 5 carbons in a chain, B has 4 carbons with the 5th as a branch. So they are isomers of each other. They want the names, the International Union of Pure and Applied Chemistry, for A and for B. So what are those names going to be? Well, 5 carbons, pentane, 4 carbons with the methyl group on the second, 2-methyl butane. Then they said explain the term isomerization. Well, it's changing long straight-chained molecules into shorter branched molecules that have the same molecular formula but different structural formula. Long and straight into shorter branched molecules that have the same molecular but different structural formula. They want to know, predict, does A or B have a higher octane number? So which of these would go for the higher octane number? Well, this guy's long and straight. That's generally not good. This guy's shorter with a branch. That would be good. So B has a higher octane number. And when they say justify my answer, it's because it's shorter and it has a branch. So again, you'll see that, those questions, we covered those, and it's not a huge amount of information in order to be able to do question 6. There isn't that much extra compared to what I've just, explained to you in order to be able to answer question 6. It does, however, always have a heat of reaction, right? Calculation involved in it. So I'm going to use this one as an example, right? 2013. And I'll be doing more of these in the Easter Crash Course because this is the topic that I also will be covering. So we'll be able to do more examples or, have it again so that it, further, clarifies it in your mind. All right. But here we're looking at ethyne is produced from calcium carbide and water, and they've given me this balanced equation. Ethyne we get from calcium carbide and water, and they want me to calculate the heat change for this reaction. They want me to find the heat change for that very reaction. And we've been given the heats of formation of. We've been given the heats of formation of 3 things, folks. Actually 4 things. I've been given 4 pieces of information. I've been given the heat of formation of calcium carbide, the heat of formation of water, the heat of formation of ethyne, and the heat of formation of calcium hydroxide. 4 numbers, 4 pieces of information given to me. So I want the heat change for this equation, and I've been given the heat changes for these 4. Now, there are different ways of approaching this, and if you're mathematically minded, well, doing the method that doesn't involve writing any equations is great. But I often find that there's a lot of the class is not necessarily mathematically minded. So I do mine, I suppose, by first principles. I do it from scratch. So using my equation, I'm going to copy down what it is that I want. So this, as I said, is 20, let me find it again, it's 2013, and it's question 6, and it's part C. So I want the heat change CaC2 plus 2H2O to give C2H2 and CaOH twice, and I am looking for the heat change for that reaction. That's what I want to find. I have been given 4 pieces of information. You don't have to number them, but I am. So I've numbered them in my question, and I'm going to number them as I go through them. The first one of those is they want the heat of formation of calcium carbide. Now, heat of formation of calcium carbide. There's calcium carbide. I want to form it, so it goes over there on the right-hand side. I want to form it from calcium, which is Ca, and carbon, which is C. They are its elements in their standard states. The calciums are balanced, but I'm going to need 2 Cs for the calcium carbide. And I was told the heat change for that reaction is minus 59.8 kilojoules. That's what they gave me, that information. Second piece of information, heat of formation of water. So they've given me the formula for water in the equation, but I surely know the formula for water. So I'm forming it, I'm making it. So water goes on the right-hand side because I'm making it, I'm forming it. And the elements are hydrogen and oxygen. Now, neither hydrogen nor oxygen can exist on their own as single atoms, so it's H2 and O2. and I'm going to have a half an O2, because if it's a heated formation, I just want to make one of them, 1 mole of them. And again, the question tells me in it that it's minus 285.8, minus 285.8 kilojoules. Third piece of information I was given in the question was heat of formation of ethine. There's your ethine. I want to form one of them from its elements, carbon and hydrogen. So that'd be 2 C's and a H2. And the heat change there, I was told, was 227.4. Now, if your heat change is negative, it's exothermic. The reaction loses heat, minus for loss. If it's positive, it's endothermic. The reaction is gaining heating. Or gaining heat, sorry, and you can put the plus sign in, plus for gain. And then the last piece of information I was given was the heat of formation of calcium hydroxide, Ca bracket OH twice. And remember, all of these formulas are in the equation. I'm just forming them. So that's going to be calcium and oxygen, which is O2, and hydrogen, which is H2. So there's 1 calcium, 2 O's on each side, 2 H's. So that's balanced. And my heat change for that reaction, they told me, was minus 985.2. So all I've done is copy down the information I was given. So here we go. I want one of these on the left-hand side. Here's one on the right-hand side. I'm going to reverse that equation. I'm going to write it backwards. So I'm going to start with CaC2, and I'm going to make Ca and 2 Cs. And the heat change, have a look, was minus 59.8, but now it's going to become plus 59.8, because when you reverse an equation, you reverse the sign. It was minus, now it's plus. I would like 2 waters on the left-hand side. This guy's got 1 water on the right-hand side. This guy needs to be reversed and times 2. The whole thing is reversed and times 2. So if I reverse this, it's going to be 2 H2Os to give you 2 H2s and an O2. And the heat change, folks, is going to become plus 285.8 times 2. Don't forget, times 2. Everything by 2. I want 1 C2H2 on the right-hand side. I want one of those. There's one. That guy, we just copy it out. We don't actually have to change it in any shape, manner, or form. So 2 C's and a H2. Little hint, folks, try and keep your arrows underneath each other. It allows you to see what's being made and what's being used up. It makes it easier for you to see if you've arrows scattered all over the place. You're trying to remember, is that left, right? Do you know what I mean? So try and keep your arrows underneath each other. Not in terms of I'm encouraging you to be tidy. This is for your own benefit. In a few minutes, it'll be easier for you to look at your question if you do this. So that I made no changes to, so it's plus 227.4. No change made to that guy whatsoever. And here we want a calcium hydroxide on the right, and this guy is a calcium hydroxide on the right. So don't have to change him either. He's just copied out CaO2, H2, arrow to give you CaOH twice, and the heat change for that minus 985.2, and off we go. Now, the reason why I do it this way is because if I've made a mistake, it's going to show itself up next. Because I'm now going to be able to cancel out things from left and right hand side. So whatever energy was involved in making that calcium on the right, it cancels with that calcium on the left down there. So they're gone. Whatever energy was involved in making those 2 carbons on the right, they're knocked out by those 2 carbons on the left. So they're gone. Whatever energy that was involved in making that O2 on the right is knocked out by the O2 being used up there on the left. And whatever energy was involved in making those 2 H2s on the right, well, they're knocked out by that H2 and that H2, so you can combine on the left. Now, if I have done everything properly, I should be left with exactly what I wanted. So I wanted a CaC2, I have one CaC2. I wanted 2 H2Os, I have those on the left-hand side. Nothing else on the left-hand side, so arrow. I wanted a C2H2, there it is, left on the right-hand side. And I wanted a calcium hydroxide on the right-hand side. And there it is. Now, here is what we call Hess's law in action. This is a reaction happening in one stage, and we didn't know its heat change. We were looking for it. This is the reaction happening in several stages. Several stages. And Mr. Hess said, if you add all the heat changes for the individual several stages together, you'll get the same heat change as if the reaction happened in one step. So if I add all of these numbers up, I will get the overall heat change for that. Now, what's more important in a marking scheme is you're going to get 3 marks for working plus 59.8. You're going to get 3 marks for having 2 times plus 285.8. You're going to get 3 marks for leaving that guy alone and not making any changes to it. And you're going to get 3 marks for leaving that guy alone and not making any changes to it. So now I've got 12. And if I add all of those up, I'm going to get my final 3 marks for my answer. If I get one of these wrong, well, that means my answer is going to be wrong. So I go from 15 down to 9. So the important thing is not to get one of those wrong. So these heat of reactions every single year.
Watch
every
this.
year.
And how did I didn't have the time to raise my thing.
Sorry, folks.
No, I didn't.
You could just turn off a microphone
because
there.
she did.
You don't
Because
mind?
she did.
Maybe I can turn
Are you
it
about
off.
to cry?
No,
You
we're
baby.
not. Sorry, folks. This can happen, unfortunately. So we will mute. Thanks. Okay, so this is our, what you call it, Hess's law, and there was one every single year except for 2007. Now this syllabus came up in 2002, folks, and we're all the way up to 2024, and that means that there are 20 something years for you to practice. So you can pick any year other than 2007, and you will find one of these questions, and you need to practice them. Now, if you can get all 20 something years of them done, sure, that'd be amazing. If not, I'd be aiming to get 7 or 8 of them done. Just pick a year at random, and go for it. Final thing, folks, before I go on and start looking at questions, and again, do you know what I mean? This information will be in the handouts that are going to be sent out to you because you signed up, do you know what I mean, to this session, right? In recent years, they like asking you about hydrogen as a fuel. Right? So in recent years, there's been quite a few questions about hydrogen. Now, they tend to be pretty repetitive, so here we go. Advantages of using hydrogen as a fuel, right? Make sure that we know, what you call it, 2 of them. What's an advantage? Well, it burns in oxygen and gives you water. So it's a clean fuel. You're not getting any toxic gases from burning hydrogen as a fuel. It burns in oxygen and it gives you water. That's all. You're not getting any of these toxic gases, so we don't have to, what you call it, worry about that. What else can we say about hydrogen? Well, it's got a high kilogram calorific value, so you get quite a lot of energy from it. So lots of energy released. So as a fuel, that's good, that you're getting a lot of energy being produced. Disadvantage. Sorry. Disadvantage of hydrogen as a fuel. Well, it's highly explosive. So it's not stable, right? And I'd like my fuels to be stable. So it does burst into flames, do you know what I mean? Right? Obviously, if you ignite it or produce enough energy. So it's highly explosive. Okay, so that's not good. Right? It's a gas. So, it's difficult to store. If you're going to store it, you're probably going to store, S-T-O-R-E, sorry. You're probably going to store it under pressure. And if you're storing gases that are highly explosive under pressure, well, that's not good. You know what I mean? That's not an advantage. That's definitely a disadvantage. And if it's a gas, it's also prone to leakages. Right? It's difficult, do you know what I mean, to know when it's leaking or not. Now, they like asking you for commercial, and I'll stop after this, folks, commercial methods of making or producing hydrogen on a large scale. So commercial means industrially. How do they make hydrogen? Now, we came across one of them there today, which is dehydrocyclization. So if you carry out dehydrocyclization, we changed our long straight into cyclic, cyclic into aromatic, and we got hydrogen gas as a bonus. So there's one way of making it. Second way, if you've done the chapter on electrolysis, well, electrolysis of water. That's you splitting water up using electricity into hydrogen and oxygen, right? Hydrogen and oxygen gas. So you're getting your hydrogen gas that way. That should be an S, all right? Okay. Electrolysis of water. Third way, which you've probably met if you've done the chapter on chemical equilibrium, which is called steam reforming of natural gas. So that's where you take natural gas, which in this part of the world is mainly methane. You react it with steam, which is hot water. You make carbon monoxide. That's a pity because that's toxic and poisonous, so we'll have to deal with that. But we get 3 H2s. We get 3 hydrogen molecules. So that's a good payoff. You're getting 3 H2s, 3 hydrogen molecules from 2 reactants. So if you knew your advantages and your disadvantages of hydrogen as a fuel, if you knew the 3 commercial ways, they generally have only ever asked for 1 or 2, they've never asked for all 3 at the same time, well then you'll be doing well in that particular topic. So I'm going to stop sharing my screen, folks, and I'm going to go back and see, does anybody have any questions in particular that they want to ask? And if I stop sharing my screen, you should start being able to see me once again. Yes, you're going to be able to watch it back. It is recorded. Okay. Where can we get the handout? It's going to be emailed to you. All right. Okay. At the end of this section. Isooctane, is that acceptable? Isooctane is, but generally they'll ask you for its IUPAC name. So therefore we need the 2,2,4-trimethylpentane. 2,2,4-trimethylpentane. Isooctane, right? Okay, that's that one. What was the definition for autoignition? Early explosion of a petrol air mixture. Early explosion of a petrol air mixture, right? Caused by increased pressure in the engine because the petrol is of poor quality. What are the advantages of hydrogen? They were the fact that it's a clean fuel. When you burn it, you get water. You just get water vapor. You're not getting any toxic, poisonous gases like burning petrols or diesel or anything to that effect, right? So that's good. Okay. And what else can we say about what you call it, hydrogen? When we burn it, it's got a high kilogram calorific value. High kilogram calorific value. They don't ever ask you to calculate the octane number, but they regularly ask you for who are the 2 reference hydrocarbons and what are their octane numbers, and the fact that they're comparing every fuel to a mix of those 2 reference molecules being burned. Right? So stoichiometry, moles, calculations, volumetric analysis. Sure, you know what I mean? We'll see. I do stoichiometry and all of that in the crash courses and the weekend classes, but who knows, right? If there is a demand, do you know what I mean, for it, we can always do another one of these. Will they ask the full name of MTBE? I have a feeling that they may have done once back in the early 2000s, but I'm not so sure that they'd go for that really anymore. They do, again, it was the early years when they asked, what do the letters LPG stand for? But, you know, these kind of, things can pop up again if something's come up once. Is there much benefit doing more than 8 questions? I would say no. Right, Savani, I think is the name there. Right, I would say no. I would take my time to make a good choice of 8 in the first place. And if I make a good choice, well, then there's no need to do a 9th question, because if you'd liked it, you'd have chosen it in your first 8 anyway. So I would say do it properly. Right, do it properly. 22 H8 in your mocks. What do you think is a realistic goal? If you set your mind to it, Victoria, I have seen people bring that up by 30, 40, do you know what I mean, percent. What you have to do is focus on the areas that are always guaranteed, like this one, question 6. Do you know what I mean? Like volumetric analysis, question 1. Like your other organic chemistry. I'll be putting massive amounts of what you call it, my time into organic chemistry, Victoria, you know. So I'd be learning how to draw and name the molecules. I'd be doing all that stuff. That would be good. Looking at the topics that are always on the paper, learning your definitions, they're worth 20 to or 10 to 20% of it. Titrations predicted, well, who knows? I mean, you're mad if you don't do them all. It is unlikely, William, all right, that they are going to ask you the titration that came up last year or the year before. Right? That is highly unlikely that that's going to happen. All right, okay. So whatever vinegar, do you know what I mean? Whatever isn't. Just to say that ones that haven't appeared recently, it's been a while for water of crystallization. It's been a very long time since iron tablets, do you know what I mean, has come up. And your water experiment on Winkler hasn't appeared in the last 3 or 4 years either. So I'd be, you know what I mean, I'd be going for that. I do have a list of definitions. Right, I'll send that on and that can be sent on to you too. I can't say that they're definitively every single definition under the sun, but it is one done by topic that I give out to my students just to help them revise something that you could be looking on coming in and out of the bus or the car or whatever in the morning when you're not having wonderful conversations with the people sitting beside you or whoever is driving you in, like my children do. And are there any more free masterclasses scheduled? You'd never know. We might be able to do a few more. Will I be docked marks for not drawing all the bonds in hydrocarbons, like using CH3 instead of drawing them all? As I said, it's a pretty new thing. And the information I've been given is they will want you to draw all the bonds all the time. So the question will probably say all the bonds. You know, that's how they're going to do it, right? All the bonds. That's what they've done in the last year or so. So therefore, you should do that. List of definitions, is that what you're asking me for? Yeah, I mean, it'll be sent out to everybody. So I'm giving you the handout on fuels. I'm giving you my total handout on heats of reaction with all the other stuff that you need to know for heats of reaction as well. And I will send that definitions handout on for it to be sent to you also. Yes, I would, focus on studying for 8 questions. Leaving topics out, anything you leave out, you're reducing your choice. You know, I suppose if you decide on one thing, let it not be organic. So I would get people going, what about electrochemistry? Well, going on past history, it's been half a question only, maximum half a question. If you are prepared to live with the fact that it could be a full question and you're happy enough to go for choosing 8 questions out of 10 instead of out of 11, well, then that's fine, as long as you're well prepared for the other ones. Again, you know, there are certain areas, organic, atomic theory, and volumetric analysis. When I knew all of those, I'd be going for equilibrium, water, and rates, and they are the main areas to concentrate on. Option topics, you see, if my thing with the option, it's 31 marks guaranteed, but it's only 31 marks. So if it's going to take you 5 hours to learn for 31 marks, imagine if you put that time into organic chemistry, where organic chemistry is going to be worth about 160 marks on the paper. Now, it really depends on your individual, do you know what I mean, situation. But I'd be putting more time into topics that are worth more marks. And remember, your options are going to come up in questions that already have a choice in them. So you can still do those questions if you don't do the option. Most important, organic chemistry, followed by atomic theory, followed by volumetric analysis. When I know all of those, I would go chemical equilibrium, water, and rates of reaction. And the reason why I would choose those 3 is because you are guaranteed 1 full question and 1 half question out of those 3 chapters, but it's never been that minimum amount. So you might get 2 full questions and a half a question out of those 3 chapters, or you might get 1 full question and 2 halves. So the worst case scenario, water, equilibrium, and rates, and there are 3 individual chapters. They're not like organic where you have half a book to learn. They're not like atomic theory where you have another half of the book. Do you know what I mean, to learn? That's what I would be looking at. And I would be practicing exam questions. There is no point sitting down at this stage and just staring at notes, right? You need to have exam question out, marking scheme out, notes beside you for reference. That's what I would be suggesting. Test for anions, right? Test for anions. Yeah, I mean, it's always a possibility in question 3. It was there in 2009. If you want a good example of one, go to 2009 question 3 and see what you think of that question, right? There's lots of equations, but they generally only ask for 1. So it's all observational. What do you see? What is the name of the reagent you added? What is the formula of the reagent you added? And while there are lots of balanced equations, they generally only ask for one. Right? How many years back would I go to be confident? Well, if you're only going to do 3 or 4 years, you're not getting a mix. I'd be trying not even to go back. I'd be randomly picking. Do you know? I'd say the last 10 years. If you really want it, last 10 years. Right? The way the questions have been kind of worded and topics changed in kind of 2015. That's my opinion. I think that somebody came in, somebody new, and they're asking, do you know what I mean, topics that they like. Just like if I was setting the questions, I'd be more inclined to do topics that I like. Question 3 is up to you. I would be putting my effort into volumetric analysis and question 2, organic experiments. And sure, if question 3 was nice on the day, wouldn't that be great? If it wasn't, no harm done. So you've 27 experiments to learn in total for questions 1, 2, and 3. If you do question 1 and 2, that's 15 experiments, right? If you do question 3, you have to learn 12. So you're getting 2 questions for 15 experiments. Do you know what I mean? But to get 1 question, you have to do 12 experiments. So I'd be pushing on the first ones, question 1 and question 2. They would be the ones that I would do. Should you know how the bomb calorimeter works? You had to answer that once in 2010, give an outline. So chances are no. But they often ask you what's the name of the instrument for measuring, and all you have to say is bomb calorimeter. All right, folks. Okay, so I hope that you found that helpful. Last one there is a good question. Best way to learn experiments effectively? Every way that is best is to practice questions. Marking scheme, question, you trying it, you going, I don't know the answer. Looking at the marking scheme, learn the answer. If you don't understand the answer, use your notes. Right, okay, so folks, I hope that we're going to have to, what you call it, wrap it up. I hope that you found that helpful. The notes will be sent out to you. And as I said, we may do another one before the end of the year. We'll see if there's a demand or whatever for it. And if I see if any of you are coming in at Easter time in a few weeks' time and you're coming to chemistry or not, pop in and say hello and say that you were at this. So, folks, thanks a million for signing up and best of luck. I'm sure you'll all do wonderfully. And remember, you know an awful lot more chemistry than you think you know. So just stop, breathe, think, and write it down. Okay? Thanks, guys. Thanks a million.
Thank you.
Bye-bye. You're very welcome. Bye-bye.